Okay, good morning everyone. So let's begin our agenda today. So today we're gonna introduce what is called the dynamical infield theory, the complex set. Let's begin reading our lesson. So do you find any gap sentence?
First sentence.
Yeah. First sentence is gap sentence. And the keyword might be the network structure. So for instance, in previous method, what is called the mean-field limit on the network is based on the fault-for interaction. But the authors actually, the whole thing about dynamical mean-field theory is to generalize the network from fault-for to the other things like heterogeneous or sparse network. This is the content of today's journal. So in one sentence, we want to learn a method which effectively describes a system and see that, so if we have an effective description, we can do something with that effective description. So we will learn what can be done with this effective description. So what is effective description? Okay, so effective description is kind of a scaling limit or a multi-scale analysis. And in particular, we will learn what is called the mean-field limit, or in general, the dynamical mean-field theory. Okay. So let's begin with the basic concept of the mean-field limit. So we will gonna look at the three things. We have a system, we have a scale, and its description. Description is usually an equation. So for instance, if we have a classical dynamics or classical mechanics, so the objects that we can observe in our real life, we call this the classical mechanics. And its scale is called microscopic or particle level, like this lepton or like this cup or something like this. In terms of the equation or the description, it can be written by the following ODE or any kind of ODE we usually deal with. Yeah. On the other hand, if you want to look at smaller scale, then it is the regime of quantum mechanics. And scale is called just quantum, and the objects are the quantum particles. In this regime, the equation is no more this Newtonian equation. It is written by usually Schrödinger equation, this PDE. On the opposite side, if we want to look at a regime of very many particles, like the galaxy in our universe, then its system is in the statistical mechanics. So we no more can deal with individual particles. We instead look at the whole thing and do the statistics. And its scale is towards mesoscopy. So from the particle to this regime, we are essentially dealing with something like a gas, but it is rarefied. Rarefied means that the density is quite low, low density gas. Now the equation is usually described by this P, which is called the Boltzmann equation. So this F is a probability density with position x and velocity v. So it describes the statistics of the particles. But you can go more. So I just said that rarefied gas is a gas of low density. If the density is quite high, then you can describe you are in the regime of fluid dynamics, fluid mechanics. Its scale is called macroscopy, so fluid micro, macro, and in the middle mesoscopy. And this equation is described by the famous Navier-Stokes equation. So we have many scales, but now we are curious about the transition between each scale. For instance, you can go from quantum to classical by changing some scales, and its limit is called the classical limit. Or you can go from the particle level to this gas dynamics. So if you have individual particles and you want to go to the systems with very many particles, then it is a transition from here to here, and its limit is called the mean field limit that we want to deal with in this journal. And finally, from statistical mechanics to fluid dynamics, I perform a limit which is called the hydrodynamic limit. And there are many, so all of these things are the scaling limit or the multi-scale analysis. So there are many vocabularies regarding this kind of limits. All of these describe very similar things. I mean, have a very similar philosophy. So now we want to focus on the mean field limit among this kind of scaling limit. So from the particles, so if you imagine you are in a highway, there are many cars during the national holidays, there are many cars, then it is often more effective to see this as a motion of rarefied gas, the gas with low density or fluid. Then we have to perform some limit. Here we want to do mean field limit. So it is kind of sending the number of particles to infinity, n goes to infinity. Okay. So mean field limit is n goes to infinity. So why do we do this? So I wrote here. So usually the systems like interacting particle systems like neurons in our brain or the stars in the galaxy, they are described by the n number of ODEs. But if it is too many, like 10 to the 10 or 10 to the 18 or something, then it is too much complex and costly to compute numerical or even calculate or do the analysis. So it is often more effective to have some approximation. And in this case, as I just introduced you, this kind of interacting ODE can be described by a single PDE like this. So where F is a probability density. And this is the mean field limit, and do this by n goes to infinity. If you are curious, you can study this very well written text. So in a single word, ODE system with a very large number of particles can be described by a single PDE. So we are satisfied. Yeah, so let's study a little bit more. I will introduce you a little bit more of the concepts. why this is possible. Let's go back to the continuity equation. Maybe you have heard of this many times, such as in Woodin Choi's lecture about goal matching or something. If you have an ODE like this, x prime is equal to f of x, you can translate it by a single, PDE over density. What does it mean? So, these two are equivalent in this time. So if you have an ODE, if you choose an initial data, you have a trajectory. So if you choose that initial data, you have different trajectory. If you have different initial data, you have different trajectory. However, the PDE philosophy, you start with a set of initial data, and see its dynamics. And this ODE is now a dynamics over density. So that is why it is written by right-hand side PDE. These two are equivalent. You can do this also with the interacting particle system. If you have an n number of ODE like this, interacting with the function v, you can also write the continuity equation. So this is just the same thing. Here, mu is now a density of n particles, like this. So now, how to perform a mean field limit? I will briefly explain you this. Okay, so in order to describe effective equation, you take the marginal distribution. So you integrate over the x2 to xn, so only x1 remains. Then you also need a second marginal, so integrate over x3 to the remaining thing. You have a two-particle marginal distribution. Then if you write down the equation of this first marginal, then you have something like a PDE, which have mu1, but some other term about mu2. So the equation is not closed with mu1. It is not an equation purely by mu1. You also have mu2, so you cannot reduce at this moment. So in the end, you have to assume something, which is for the molecular chaos. But why this name? And what does it mean? Molecular chaos assumption means that as the number of particles increase, it's too large, then we assume that particles become chaotic. But if you record what is chaotic, chaotic means that sensitive dependence on initial data. In other words, if initial data is different, then the trajectories are very different. That means if the initial data are different, trajectories are independent. So they are not correlated. So they are decorrelated. In other words, the marginal distribution of two particles can be decomposed like the first marginal. Okay. Intuitively. Then at the end, you can write this annoying term by you can decompose mu2 by mu1 and write down a single PDE of mu. This is one step, typical step for the mean field limit. So you can observe that if you observe the continuity equation, although it is PDE, it is linear in mu. Okay, linear in mu. If you record you may record the Pufman operator. Pufman operator linearizes the dynamics. It is similar to continuity. However, if you do the mean field limit, you have mu here, f of mu, like by this complicated interaction. So it is non-linear in.
So in this equation, x, what is the meaning of x?
X here. Yes, position. So
we have n dimensional position.
no. This is a single dimension. And so if you start with NOD, then you have a dynamics of N particles. Let's say it is on R2. You have dynamics. Then you have now view of X, and here X is also in R2 or any Rn that I designate. Then it is about like this. So it is the probability density of the possibility that X lives in. Same dimension with individual particles. But the serious restriction of this whole process is that it assumes the word-to-word interaction. So it assumes that every particle is essentially the same. You cannot distinguish. And also, there is no network structure in this equation. So but in real life, we have more complex networks. So we need some other things. So this is a general interacting particle system. You notice that we have a coefficient Aij. So it represents the network structure or something like adjacency matrix. But if you just recall, the mean field theory does not have that coefficient. So it assumes the orthogonal network. However, in real life, we have different networks like this, or such as sparse network, modular, or heterogeneous network. So in order to overcome this limit, the dynamical mean field theory is introduced to deal with this kind of equation. But it is not easy. So there should be other assumptions, such as, so most importantly, we rely on randomness to impose some randomness on the network, and even the randomness of the initial data. Sometimes randomness makes the problem easier. So now, so if you add the word dynamical, then maybe you can deal with the heterogeneous interaction.
So the randomness means the randomly the network
Yeah, randomly changes.
changes.
Not according to the time, but you have some. So network is a random variable. So
So maybe describe some expected
yes.
dynamics with some randomness.
So, but one remark is that this mean field theory is very rigorously developed mathematically. But this dynamical mean field theory is not uniform and not very rigorously developed. So it is usually done by physics community. But recently, people are studying this dynamical mean field theory in a name called graphling. So for instance, let me give you a brief overview of dynamical mean field theory. You want to study this interacting particle with Aij network, and we assume some Gaussian distribution on the initial data. So its expectation, initial expectation is 0, and you have this variance sigma squared. Okay? This Dirac delta means that if Ij is different, then they are independent. If they are the same, then xi squared is sigma squared. So you have the variance or the standard deviation. You also impose some assumptions on the network. In particular, we have skew symmetry on the network like this. And you also have some kind of Gaussian statistics. Now, if you perform the mean field limit, I will just give you the result. You obtain a single ODE instead of the n number of ODE. It's very complicated looking formula, but if you are familiar with this integral term is like a memory effect, non-Markovian dynamics. But here, what is phi and nu? They are very complicated. Also, phi is also some random term whose expectation is 0, and it has some following so some Gaussian distribution where J1 is very what is called the Bessel function. It has some form, you can just ignore it at this moment. Also, nu is written by some complicated form where this theta is a heaviside step function. You don't have to focus on its exact meaning right now. So intuitively, how do they do this? If you have this interacting particle system with very complicated network, you choose one particle randomly. Then you separate the effect of forces in central to that particle. So here the left one is forces without that particle, and the right hand side are the forces coming from that particle. Then at the end, the forces without each particle becomes the source term phi that is applied to that particle. And here it becomes something like a force to itself. So that's why it becomes something like a memory effect. This is one kind of dynamical mean field theory. So if you are curious about the detailed derivation, you can study this article. So it says it is written for biophysics community. So maybe it can be helpful. Okay. Now we can go on to our main text. So as I mentioned, dynamical mean field theory is not uniform. So there can be many various derivations and concepts of dynamical mean field theory. And this paper presents one another concept. Okay. Still, the dynamical mean field theory I just presented is not complete. Why? So, if you start with the interacting particle system, again, the mean field theory assumed all-through interaction, the traditional mean field theory, and the dynamical mean field theory I just presented didn't assume the all-through interaction. However, they assumed some skew symmetry on the network. So, in order to study a different network structure, they also, the authors presented yet another generalized dynamical mean field theory. So, the network that the author studies is the following. So, you have a following type of differential equation. The authors want to study sparse, directed, and random network. I will explain you this one by one. Okay, so it is directed. So here the network is decomposed by Cij and Jij. So Cij is the network structure, and Jij is a strength, network strength. So Cij is either 0 or 1. So 1 if there is a force coming from J to I. Okay, J to I. And 0 if there is no edge. For instance, we have this picture. And there are two notions. So since the graph is directed, you have two kinds of degrees, in degree and out degree. So in degree Ki means that the forces coming to the I, so to the node I. So if you look at this formula, it's you sum up by j, the index j. Cij means a force coming from j to I. So if you add all the j, then it is the n degree. On the other hand, if you add j of this term Cji, okay, Ji, then it is the edges coming from the node I. So it is called out degree. Okay. So now I impose some randomness on this whole network structure. So how do we generate the random network structure that the authors deal with? Let me briefly tell you this step by step. Okay, first, so you have to do two things. Aij is C and J. So you have to deal with C and J. First, J. The coupling strengths are identical and independently distributed. Drawn from some distribution you choose with mean and variance. Okay, so randomly choose the coupling strengths. Next, you also choose in degree and out degree. In degree and out degree from some random distribution. They are also IID. But the thing is that the expectations of in degree and out degree are the same. So this is the assumption. They are the same with the number C. And so the network structure, this paper deals with is sparse. What is sparse? This expectation or the average C is independent of n. So even though n is very large, C is fixed. C is still small. This makes you sparse. And finally, this network structure follows following the complicated distribution. So this is the probability that the whole Cij satisfies some value. So it is something like this. For instance, it is something like probability that C11 is given to. So diagonal element is 0 to make sure that you don't have any self interaction. So suppose you want to know this kind of probability. That is the meaning of that notation. And what is this? So let's look at one by one. If you look at this Dirac delta here, this imposes you that the Cij, actually the in degree satisfies this number, Ki, because you already set the Ki and Li drawn from this notation. You make sure that in degree satisfies Ki. Here also, the out degree should satisfy Li. They are in degree restriction and degree restriction. What is this? So it means that Cij is 1. The probability that Cij is 1 is approximately C over n. So intuitively you set Cij to be 1 with probability C over n. But there is warning. So it looks fine, but if you really want to generate such network, this formula does not really helpful, I think. So you can do some other computational algorithm to generate such network. So, but let's focus on the analytic aspect. So now we have a network. We constructed a network. And now let's go to the effective equation. Okay. But so far, if you recall it, mean field theory has single PDE as an effective equation, and dynamic mean field theory has random ODE. So all the effective equations are all different. Now we will have yet another different expression for the effective equation. I want to say there's no equation in this setup. So what do we have? So our original system has the following n number of ODs. In other words, we have n degrees of freedom. Language in physics. Instead of an equation, we have the probability of the trajectory. It is called the path probability. Please ignore this. So now we have an effective equation. I mean, it's not really an effective equation. So we have some kind of probability distribution of the trajectory. So what does it mean? So if you have an ODE, you expect that you can, if you solve it, you have some kind of trajectory like this. And if you have a usual meaning of probability like this, random variable, it means that x is some kind of x is located in this x is equal to 1 like this. But here, the path probability means that instead of a number, you have a whole trajectory like this. So you compute like this. The trajectory satisfies something. Probability that the trajectory is drawn like this. This path probability. So what do we do this? So if you have a probability, then you can compute the moment or some average of some quantity that you are interested in. For instance, you can compute the moment of x times x to the n. So if you set n is equal to 1, you have the mean trajectory of the average trajectory. But here the dx is very unusual. It is called the path integral. I will explain you briefly. So intuitively, okay, so if you have a trajectory, the path integral means that you integrate over the whole trajectory. But this is counterintuitive. How to understand this? You first study the discretization. For instance, if you have 6 numbers, then this integral is approximately an integral of 6 variables. Now you send the limit goes to the number of points to infinity, and you have the path integral. I will explain, I will give you a brief example of computing this path integral later. Okay, but before that, let's study what can be done using this path probability. So, from the original system, you can compute the moments. First moment is the average, second moment is something like a variance, fluctuation. But using the path probability I just mentioned, you can also compute the first and second moment by using the path probability P and P by the path integral. In order to see that this effectively describes the system, the authors compared the path probability, the solid lines are the moments computed using the path probability, and the authors also computed the first and second moment using a large system where n is equal to 4,000. And these are the this point shows the standard deviation the particles with the original system, and the solid lines are the macroscopic variables. And the left-hand side and right-hand side differs as you vary the in-degree distribution. I mean, essentially they are the same. I mean, they give us the same comparison. So you can see that these solid lines accurately captures the real dynamics with large n. Black, green, and red are different because the systems they choose are different. Okay. So in other words, effective probability, test probability effectively describes the original system. Maybe you can recall something like QSSA or other multi-scale method. They eventually want some effective equation that simplifies the original system. This was the first moment. This was the standard deviation. Q, second moment minus square root of the first moment. Also, they pretty much captures the real dynamics. Okay, so we are all done. So let me briefly give you a concept of test probability. Assume that you want to compute following integrals. dy, you notice the path integral, integration over the trajectory. So, but you have a restriction that the trajectory starts from the same value with this end point. So, if you start with y0, you end up with the same thing. So, with this closed path, and you want to integrate the following exponential terms. Do you do? You first discretize the path with the restriction of the initial and final value, and you obtain in instead of I, and you integrate over this n-1 number of variables, and you also have to discretize the term inside the integral, and it can be discretized as follows. And actually, if you rewrite this, you can notice that, this is a quadratic form of the variables. So you have actually squares and yk plus 1 squared, in other terms, quadratic terms. And you can write it like this, where actually k is a discretization of this Laplacian. So if you record, if you look at some calculus textbook, you have that this integral is proportional to the determinant of k to the minus 1 over 2. Then if you extend the limit, you can finally have that this path integral is a determinant of this operator Laplacian. But you can compute the eigenvalues of this Laplacian so that you can compute the whole integral. So this is a process of path integral. Okay. So now, even though I give you some results of the path probability, I didn't give you the exact formula, so I will just quickly mention the exact formula of the path probability that this paper presented. So if you start with the original system like this, then the effective dynamics is like this very complicated formula. So what is this? If you look at this red term, it is kind of a Dirac delta, imposing that the x, the trajectory x, satisfies the following equation. So it is almost the same thing with the original system. Not the same, exactly the same thing, but pretty much the same. And you also have that the coupling strength should also have some restriction. And finally, you also have to sum up over this in-degree distribution. So basically what this do is for each randomly sampled k, instead of considering the 4 number of particles, you start from small k equals to 0, 1, 2, and study this term step by step. This is very complicated. You can ignore it. But you can see that actually this does not give you the exact formula. This is the equation instead of the formula. Because you have px here and px also here. So actually this is the equation you have to solve. Still it is not very easy to obtain the true answer. You have to solve this fixed point equation. So, so far we see that the effective equation well describes the large number of systems. But what can we do else? What can we do else? Wait, I will tell you. Using the effective equation, we can do something more. So, what is the advantage? One advantage may be computationally tractable. So, if you have a large number of ODE, it's very difficult. But if you have an effective equation, it is easier. The other thing is that you can actually study the effective equation and derive some analytical result. For instance, if you have this system, you can notice that here interaction is tangent hyperbolic. So if you put x equals to 0, the right hand side is 0. So 0 is a fixed point. Now, if you have a fixed point, you want to study its stability. How to study stability? The authors used effective equation. Because spectrum or the eigenvalue of this network, although I don't know much about random matrix theory, but it is known that this large random matrix eigenvalues can be studied in the asymptotic regime. So using that, the authors find the stability condition that if the sparsity, so the average in degree note, is less than some critical value, defined like formula, then you have a stability. So, okay. Here, the authors, from top to bottom, they decreased the sparsity slowly. And here, the sigma j and mu j come from the distribution of the coupling strength. They are the mean and variance of the coupling strength distribution. Anyway, the thing is that you can compute the threshold. Actually, the authors choose mu and sigma like this. Then if you compute this, you can finally compute the threshold becomes 3. Now if you even observe this graph, that's time equals 80, you can observe that below the blue line, the trajectory seems to converge. The other things maybe looks flat. Why this happens? Actually, the blue line is when c is equal to 3. So it's the threshold. If the threshold is less than 3, the average trajectory converges to 0. And 0 is the fixed point. So it means that 0 is a stable fixed point. So the lesson is that effective equation, you compute some parameter values which gives you a stability. And you can do many other things.
So in the point of view, regarding the network structure, if the C is long, when the C
Okay, so in summary, there are many words. Effective equation means simplified equation. How to obtain it, the way to obtain it is called by many names. Here we studied infield limit. In general, it can be scaling limit, multi-scale analysis. In particular, if n goes to infinity, it is called the infield limit or dynamical limit. I have to say that if n is small, it is meaningless to do the infinity. It is for large n. And for the orbital interaction, traditionally, we have a single PD, both probability measures, distributions. And if you have some heterogeneous interaction, you obtain some random ODE, single ODE. Finally, in this context and in this text article, you have a path probability instead of a single equation. Okay. Thank you very much. Any questions?
Thank you for your lecture. And I have a question regarding the slide for DMF.
And well, Microsoft
12 slide.
term slide. Can you tell me DM
The dynamic infield limit.
number 12?
Number 12. So, if you, I can understand the Gaussian fluctuation of the initial data. Could you explain the Gaussian fluctuation network?
Also, I felt a bit uncomfortable with this expression. I think maybe you have to impose this, take consideration of this. Maybe you know that if the indices are different, then it becomes zero. You know.
Yeah.
So let's say if I is different from k, then here it vanishes. And
IJ, I equal to A, and K equal to L.
yeah.
스큐 만들려고 좀 하겠습니다.
네, 이렇게 한번 식으로 설명하려면
순서가 IJ 순서가 똑같으면 앞에 안 되면은 뺄게요.
그럴 수도 있고 여기에 그냥 미미 스큐 시메트리를 적용하면 A, LK랑 비교하는 거나 다름이 없는데 그러면 I랑 L도 다르면 여기도 날아가고 약간 그런 식으로
아니 다르면 뒷부분이 날라서 부호가 반대가 돼. 스큐즈.
네, 그러니까 결론적으로는 어쨌든 이런 걸 보장하고 싶은 것 같아요. 이렇게 인덱스가 만족되지 않으면 그냥 명들고 제곱만 시그마식으로
그러니까 IJ, JI 순서 바뀌는 거 아니면
자연.
같은 IJ면 포지티브 반대면
반대면 저희 스큐즈가 지금 가지고 있습니다. So that means we have not only randomly connected, but also each edge weight differ change over depending on time.
wait,
No, time.
no, not depending on time. I mean this randomness does not depend on time.
comfortable.
Think that 랜덤하게 generate 된다고 expect.
fixed generate. So then in the top of the left equation, laptop equation, the second term describe the interaction, right? Interaction.
The integral
Yeah, integral.
interaction. It's more like self interaction, so memory effect. I mean, because we reduce the original system. The interaction is really comes from phi, the first phi.
The original midfield,
Yes.
the variable was distribution.
Yes.
But for the heterogeneous case, this was a variable.
Wait a minute.
Page 12. Here. So, what is the variable for this dynamical midfield?
You mean x?
Yes.
So that x is lives in the same space with xi.
So it's the location, maybe state of each particle.
Each particle, I mean one particle, but they are randomly. I mean this randomness is reflected in phi and 하나의 파리클 다이나믹스로 대신을 하는데
네.
대신 얘네가 막 랜덤하게 바뀔 수 있다는 걸 염두에 둔 것 같아요. 그래서 그런 게 약간 유도 과정에서 반영이
그러니까 분포가 아니라
공포가 아니
스테이트로
네.
하는데
근데 랜덤니스 때문에 걔네가 약간 춤춰준다고 생각하고
그거랑 좀 다른 거죠. 약간
처음 그거랑 다른
처음이랑도 다르고 약간 센트럴 매스 뭐 그런 거랑 상관이
그것도
또 아닌 거고 되게 물리적으로 정의 내리기 어려운 느낌은
네. 유도 과정을 보니까 그럴싸한 것 같아요.
Yeah, here still some random particle here and the next is path probability.
Yes.
So is it defining probability of each path?
Each path.
Each path. So the probability space is the collection of paths.
Yes.
And we can derive the equation for that. Yes, last. So original mean field was distribution of particles, but here it's the probability of paths.
Second and third, yeah, I think they share the same philosophy. One